One of the great things about graphical models is that you can very easily determine for two sets of random variables whether they are conditionally independent given a third set. And in a little bit, in a few videos, or in a video or two, we're going to look at the D-separation property, which is just an extraordinarily simple trick, or it's simple to apply trick to determine that sort of conditional independence. And in order to build up to that, in the next video or two, I'd like to go through a couple simple intuitive examples of how that plays out in some very simple graphs. So first, let's think about just some graphs with three random variables, just some nice and simple graphs. So let's say we have random variables a, b, and c, and that the distribution on a, b, and c respects this graph. So let's write down what that means. That means that the joint probability of a, b, and c factors as the probability of a given c times the probability of b given c times the probability of c, right? That's what it means that a, b, and c, their joint distribution respects this graph. So now let's think about if we condition on c, what happens? So what is the conditional distribution on a and b given c? And let's denote the fact that we're conditioning by filling in c here. Switch back to my pen. So what is this? Well, this is just the probability of all three of them divided by the probability of c. And if we plug in this formula above, the probability of c cancels, and we get probability of a given c times the probability of b given c. And so therefore, well, let me put it down here. Therefore, a and b are conditionally independent given c. That's what this notation means. A and b are conditionally independent given c. That's what this implies. So in this, when we have a graphical model that looks like this, then we know that a and b are conditionally independent given c. And let's just call this case 1. And we might refer to this as a tail-to-tail relationship. That is, the arrow going to a from c and the arrow going to b from c, they are tail to tail at the node c, where this is the tail end of the edge, and this is the head of the edge. So let me give you a little maybe sort of real world example of this. Any real world example is going to be a little bit contrived. But so this is something which has happened to me recently. There's the apartment that I live in has an oil furnace for the heat, and so it's got a boiler. It boils the water and makes steam, and it goes through the pipes, and that heats up all the units in the apartment building. And when the boiler kicks on, sometimes as it's running, I can hear it make a noise. It makes a low hum, and sometimes I can hear that noise that it makes. And also, sometimes when the boiler kicks on, it has happened before that it sets off the fire alarm. Not too long ago, the boiler kicked on, and I heard it making its hum. I heard it making its usual noise. And then, not too long after that, it set off the fire alarm because it backfired. It had backfired, and it sent out a bunch of smoke. And that set off the fire alarm, and that was a very pleasant experience. That was Christmas Day. Merry Christmas. That was a nice Christmas day. So let's think about this situation. Before I knew that before I knew that the boiler came on, let's think about if we didn't know whether the boiler had come on or not. then when I heard the noise, now, so after that experience, when I hear the noise, or for not long after that, several times, after that, when the boiler kicked on, I would hear the noise and I would think, oh dear God, please don't let the fire alarm come on. So hearing the noise definitely influenced my probability distribution, my estimate on the probability of the alarm going off. So these were not independent. These were not independent. The noise and the alarm were not independent, at least in my little mental model. But if I knew that the boiler, so let's say I knew that the boiler came on, like maybe, so I can, I can adjust the thermostat and I can make the boiler come on, and so maybe I knew that the boiler came on. Then hearing the noise would not affect my estimate of whether the probability of the alarm going off, because I already knew that the boiler was on, and so any estimate of the probability of the alarm going off would just be based on that and not my hearing the noise afterwards. So condition on the boiler, my knowing that the boiler was on, these would be independent. Hearing the noise wouldn't affect my estimate of probability of hearing the alarm. So that's just a little example, little real world example, sort of somewhat contrived. And by the way, so here I should say this is assuming that the probability, since whenever we're dividing by this or this conditional probability distribution, we need to assume that the probability of C is strictly positive. It's not zero. Okay, so that's our first little example. What's the next example? Let's look at another one. So if that was a tail-to-tail relationship, let's think about a head-to-tail relationship. What would happen then? So let's consider the case where we have, again, we have A, and let's put C in the middle. We're going to think about conditioning on C. So let's put that in the middle. And then we'll put B over here. So A goes to C, and C goes to B. So what happens now? Well, let's write down what this means. This means that the distribution on A, B, and C can be written as the probability of A times the probability of C given A times the probability of B given C. That's what that means. And now let's think about what happens if we condition on C. So let's condition on C. The probability of A and B given C, the conditional distribution, probability of A, B, and C divided by probability of C once again, just like before. And now, so let's see, if we plug this in directly, probability of C isn't canceling, but what we could do here is we could just pull together probability of A, so this is equal to probability of A and C, and then we could instead say this is the probability of A given C times the probability of C, and then if we plugged it in, the probability of C would cancel. We would get probability of A given C and the probability of B given C. And so once again, just like before, just like in case 1, A and B are conditionally independent given C. So at least in these two cases, we have this property that when you condition on the variable in the middle, then the other two are conditionally independent, at least in these two cases. And let me also give you an example, a little continuing our story from before. So another time, so here's another story about the boiler once again. So we know that the way that the boiler caused the alarm before was that it sent out a bunch of smoke. Another time, another time, I heard the boiler kick on, and so I knew it was coming on. And not too much later, I heard the alarm go off, but this time it was for a different reason. This time, one of the other people in my apartment building accidentally unscrewed the valve on their heater all the way off when they heard the boiler come on. And so all of the steam in the pipes went out into their room and set off the fire alarm. So that was genius. And so we know that the boiler can cause smoke or steam. I just wanted to tell you, I didn't really need to put the steam there, but I wanted to tell you that story because I thought it was interesting, was kind of funny. So it can cause smoke or steam, and either of those can cause the alarm to go off. So now let's think about what happens. So in this case, we have the boiler, which makes the smoke or steam sometimes, not always, and then that goes out into the room, and then that sets off the alarm. So before if we know whether smoke or steam happens or not, the boiler and the alarm are not independent, right? Because if I heard the alarm, I would think that bleeping boiler is doing it again. What is going on? And if I knew that the boiler was coming on, and I didn't know whether there was smoke or steam, then I might think, uh-oh, there might be a small possibility that the alarm is going to go off. So these are not independent without conditioning on this. But if we condition on knowing that there's smoke or steam, let's do that. Boom, we condition on that. Then what happens? Then let's think about, are these conditionally independent given that we know that there's smoke or steam. So say I see a bunch of smoke in the building somewhere. Then I might think, okay, it's probably the boiler going haywire again. But at that point, knowing whether the boiler is running or not is not going to affect my estimate of the probability of the alarm going off. Because if I see smoke, that alarm is going off. It's probably going to go off. So knowing whether the boiler is on or not, once I know that there's smoke or steam, is not affecting my estimate of the probability of the alarm, because the smoke or steam was the mechanism by which the boiler caused the alarm. So that was the head-to-tail case. And let me point out that if you reverse these arrows, if B was going to C and then C was going to A, then you would have the same result. A and B would be conditionally independent given C. So I could write, this would also be the same if it were like this. Okay, so these were two very nice and simple cases, and they ended up having the sort of same sort of result. But then we're going to look at the third case. So the third case that we're going to look at is we've done tail to tail, we've done head to tail or tail to head, and last we need to do head to head. And it turns out that the head to head case is a lot more subtle than the others. So we're going to look at that in the next video. Okay, see ya.